Good afternoon, y'all. And so my name is Barbara Witt, and I am doing this presentation as part of an ESTEP class called Introduction to the Atmosphere. And the purpose of this is to encourage some teachers to add volcanic lightning into their weather units. So here we go. This picture here is not the actual eruption of Mount Pinatubo, but it's actually like a precursor a couple days before, which was actually good to give warning to help evacuate people. But I like showing this picture because it's the second largest eruption, and then the kids always want to know, oh, what's the biggest eruption? And then we'll get to that later, of course. But it's a good picture to get kids thinking about weather and volcanoes because of the huge ash cloud that's up here. So it's a good phenomenon to get them thinking about, well, what's that going to do? How's it going to interrupt the water cycle? How's that going to interrupt the sunlight energy coming in, the infrared radiation, and so forth? Is it going to cause it to be hotter or colder, or that kind of thing? So it helps generate a lot of questions with the students. It's a good picture to kind of start with and to get them thinking about how other things might affect the weather besides just the basics that we talked about. Okay? So then I like to show them that the ash affects the clouds, or the ash cloud affects the weather, mainly because it does a lot of blocking of sunlight. So thick clouds block the sunlight in different areas, causing cooling. Just like if it's a cloudy day out, the temperature tends to be a little lower because the tops of the clouds are blocking some of that sunlight energy from coming in. Okay, now the really big particles, they actually wash out after a couple days. So it's a very short-lived situation. For a lot of it, after a couple rainstorms, most of that has fallen out of the sky with the help of the rain and the gravity. So after a week or two, things are kind of back to normal. There are going to be some tiny particles from the eruption that do get pulled up higher in the stratosphere, especially if it's a very violent eruption, so they get a lot of height as they go up. And as they get spread out, you might get a longer effect, weeks or months, and they might get carried by the jet stream into other parts of the world as well. So one example here, the biggest eruption that humans have kind of recorded is Mount Pinatubo. That happened in Indonesia in 1815. We have pretty good records of the temperature changes in Europe from that time, so half a world away. And they called it the world without, or the summer without a, not the summer, the year without a summer is the correct term there. And so things were about 5 degrees cooler Fahrenheit on average. And you can find a lot of graphics like this that kind of show things like that. Different novels will refer it and things like that too, so you can make some different connections. But it's just one example of how an eruption can affect weather patterns. And I always like to make connections with how does this affect the biosphere? Well, there was a lot of growing issues with crops and crop failures, which affected the humans and so forth and so on. So that's kind of one example of how a volcanic eruption can affect the weather is just by blocking some sunlight. Now, if you wanted to demo this with your students, I've got a setup over here. This is kind of just a greenhouse effect demo that I do, where I take 2 beakers, cover one up like a greenhouse with thermometers inside. But if we wanted to do something about blocking the sunlight, you could do a similar thing where instead of having like a clear covering, which for a greenhouse effect would represent like the greenhouse gases covering things up, you might do more of an opaque covering on it. And just say, let's block some of the sunlight getting through, and then compare the two different situations under the heat lamp after like 2 minutes, 5 minutes, 10 minutes, however your students decide to set it up. I tend to not give them a lot of directions. It's a pretty straightforward setup for my 6th graders, and they all kind of choose different times. I offer different thermometer choices. These are digital guys that I got fairly cheap off of Amazon. These little metal guys, they're cheap. They're cheaply made. Sometimes they fall off. The little glass part falls off, but they're smaller than the long thermometers, so they tend to fit in a lot of different containers. And then, of course, any container is going to work good for you, and maybe have the kids try different things that are clear or opaque or whatever to do that. So my notes up here, just a reminder, it's a good time to go over independent, dependent variables, making sure that everything between your 2 environments you're comparing are the same except for the thing you're testing. And then as you do that, you can kind of help, if you did some kind of 3-dimensional model for the water cycle, this might be an interesting twist too. Say, okay, let's go back to our water cycle model and let's add this ash cloud. And how does this change our water cycle model? How does it change evaporation rates? How does it change, you know, the pollution level and the clarity of the water, and how does that affect anything else? Okay, so a couple standards here. The 6th grade, the 63113, making a model, that fits in really well with there. And then for 9th graders, 92112, analyzing data to make a claim that one change to the Earth's surface can affect other feedback loops. So definitely the ash cloud affecting different things on planet Earth could be considered kind of one of those feedback loops. And it's really short, simple, quick thing to kind of hit those standards. Okay. Now, if you keep the water cycle idea going, after evaporation, you can think of the water going up and doing condensation. So I like this picture a lot that came from the NOAA website. It kind of shows that when water is condensing, the water molecules are very tiny, but they need a condensation nuclei to attach to make that water drop big enough to become a liquid, to become visible, and eventually form a cloud. And as it grows larger, to be large enough to fall down as precipitation. Okay, so again, it's a good time to review the water cycle with your students, especially if you have middle school students. And lots of different interesting graphics online that you can kind of grab to kind of show the different steps of that. But all the graphics include something that you need the water to condense on. Well, our volcanic ash cloud has a lot of surface area for this to attach to, okay? And if you have high school students, more of the ball and stick model might be more appropriate to tie in with the chemistry stuff you're learning. But something that the students should hopefully make a connection with is that the more ash and dust and smoke you have in the air, the more condensation nuclei you have, the more chances of things attaching. Of course, you have to balance that with the change of evaporation rates if the temperature's cooler and the sunshine's being blocked. So kind of where's that happy balance between those two things is something kind of fun to have the kids talk about and model. Okay? So if you want to do a model of this condensation, there's a kit. There's a lot of versions of this. This is the one I happen to have. They're all about 20 bucks in different categories. The problem is, I don't remember when I was little them looking so suggestive of drug use. So I'm not entirely certain that I would do this with my middle school kids. In fact, I know I wouldn't. But you might be able to kind of think of some different things. I'll just set my mic down here. So the kit looks like this. And there's a rubber ball to kind of change the pressure. You've got some tube and you've got a glass vial here. And to make it work, you need some water to be condensing. So I've got a beaker of water here, and I'm just gonna kind of squeeze some water up there, swirl it around a little bit, get most of it out of there. And the way it works is it's does the condensation based on pressure changes. So if I close the globe down and I seal the tube up, then the inside is sealed up and there's not a lot of air in there because I've compressed the globe, and if I let go, it's modeling a lowering of air pressure. And we see that when parcels of air go up, and as they get higher in the atmosphere, there's less air pushing on them, they're able to spread out more, and you have a lower air pressure. Okay? Well, nothing's really happening in the tube right now because there's nothing for the water to condense on. So to change that, what we're going to do is introduce some condensation nuclei with this smoke. And again, this is where my colleagues and I were like, I'm not really sure we should be doing this with middle school kids, but it does work fairly well. So I'm compressing the bulb to suck some of the smoke in. Okay, so we've got some water, we've got some smoke in there. We have all the ingredients we need to create a cloud. I'm going to compress the bulb, clamp the tube, and then as I let go, it's going to be hard to see on camera, but I see some fuzziness happening where the water's condensing on the side. And if I increase the pressure by depressing the globe, the fogginess goes away. Okay, so you can kind of make the cloud appear and disappear as you compress and let go of the globe. So it's a pretty cool experiment for the kids to try. Like I said, unfortunately, this setup kind of looks like a drug paraphernalia, but there's probably some other options out there. That just happens to be one I remember growing up. I just don't remember it acting like that. So anyway, a real quick demonstration that's kind of cool, and it might be fun to go online and find some other ways to do something similar to that. But the point is that you had to have those particles for the water to condense on. Okay. One more really cool thing that we have with our volcanoes is they can actually form lightning on their own. That you can do. That works good to help explain lightning, especially if you have middle school kids who don't have a lot of experience with opposite charges. I like using a dusting mitt. Just 1 or 2 little rubs on the balloon, and I don't know if the microphone, you can hear the static. I am rubbing the negative charges off, and so I end up with one thing that's positive charge, one thing that's negative charge, and they will very much want to be back together again. That positive and negative will be attracted to each other, and it'll stick just like magic. And you can, rub it in your hair. My hair works really good for this. Lots of times you can make it stick to a board. This is a new TV screen, smart board, so I'm not going to try it on there. But you can generally, if you give the balloons to the kids, make them stick anywhere. Unfortunately, there's kind of an increase in latex allergies, so you maybe can't use the latex balloons as a pass-around thing. But there's some other things you can do with that as well. But I like trying to explain how lightning works to students, and then when they go on to physical science, they've got a little bit of that positive and negative charge. It is an 8th grade standard now in our new Minnesota curriculum with those positive and negative charges, but it's never a bad thing to either introduce it early in 6th grade or kind of bring it back around in 9th grade as a review as well. Okay, so creating the static charge, a lot of fun. And something I like to do specifically with the balloon is after we do that, I take them to the PHET website. And this has a really simple demo. If you've never been onto PHET, it's a ton of demos from the University of Colorado. And you just hit play here. And this is pretty much exactly what I did. I take the balloon, I rub it on something, and I make sure my students understand that the negatives are moving, but the positives stay put. And as they learn more chemistry in the future, they'll realize that the negative electrons on the outside of the atom are much easier to kind of relocate and move. And those positive and negative charges want to be together. And in the sky, as all that ash is going up and rubbing against each other, we have positive and negative charges. They want to be together, and sometimes that is when they come together, they're going to make that streak of lightning happen. So it's just kind of a fun little thing. I don't even give them a worksheet anymore. We just go on there, kind of mess with it a little bit. You can have 2 balloons and do some other stuff. And then there is another one with John Travolta rubbing his feet on the carpet and creating a spark on a doorknob, which is really fun as well. But in the interest of time, I'll let you find that on your own. Okay, so this here is a video clip, just a YouTube grab, perhaps, of course you're going to rerun the commercial I already got rid of. It's a YouTube grab of lightning from a volcano. And when I was researching this, I had a lot of trouble finding good images because there's a lot of AI or retouched up or very artistic looking images. So it's kind of hard to find something real. So that's something just to keep an eye on as you're setting up your own demos and stuff, is as people are getting more artistic with stuff, just, be sure of your sources and don't just grab the first piece of clip art you see when you're doing a Google search. But there's some great video out there of lightning from different volcanic eruptions. There's no rain or anything happening, but it's just the sheer energy of the ash going up and those charges creating these lightning strikes. So kind of a cool thing you see from different, for those of us that live in Minnesota, we don't really have volcanoes nearby, so that's kind of cool. Okay, so why should you be doing these volcanoes in your weather unit? It kind of seems like a strange connection, but I think it's important to try to connect units together. So my students, when I teach weather, they've already had plate tectonics, so it's a way for us to kind of go back and revisit plate tectonics, do some review questions and that kind of stuff and bring it back around. And we spend a lot of time talking about atmosphere, geosphere, biosphere, and how everything is connected together. And that way they kind of have that basis for going into life sciences next year and so forth. So the more connections we make, the more they're going to be able to look at questions outside the box they've never seen, like on the MCA test, and kind of see like, oh yeah, this question sounds like it's about lizards, but it's really about this other thing. So just the more connections you can make, the better it is for our kids. And these videos and pictures are really good question makers. They're weird looking, they're cool, and so it's a really good phenomenon, very good to get your students to practice asking questions. Okay, some really cool extensions if you happen to have a lot of extra time, like at the end of the year. Never a problem in my class, but some people might. There's a lot of things online about how, oh, climate change is just caused naturally by volcanoes. Have your kids look into it, and they're gonna see how much of these greenhouse gases are getting put up by volcanoes and how fast does it wash back out of the air. Maybe more of a high school level than middle school level, but I think that would be an interesting project for kids to tackle. There is some really cool stuff about how this lightning from the volcanoes, how that helped change the atmosphere. And the lightning was actually the first thing to fixate the gases, nitrogen in the air, the N2, and turn it into building blocks that could have been used to first form life. So there's some very cool papers, studies, some good data that has come out recently about that. So if you've got some advanced kids or you want to make some more connections to biology, I think that's a super cool connection that I myself am going to look into more. And then also we have kind of some astronomy connections. If we have lightning here on Earth caused by volcanoes, is lightning on other planets caused by volcanoes as well? Maybe they don't have much of an atmosphere, but they do have lightning storms because of something like these volcanoes. So again, something kind of cool that some of your kids that like to ask questions and think outside the box might look into. I'm including links to where I got all my information, including ordering the lab supplies and stuff. I hope you'd enjoy my presentation. Have a great day.